Our next speaker is Beth Tellmann from Cloud to Street. She's going to talk about SmallSats and how they can be used to improve flood detection. So Beth, take it away.
Right. I'm going to share my screen. Can you see this, Sagi and Albert?
Yeah.
Okay, awesome.
Yeah.
Okay, great. I've condensed a little bit of the technical talk, and I'll kind of send you to some of our published papers for those results, because we also work a lot with the World Food Program and tried to coordinate a little bit what we really wanted to discuss and talk about at this event. So I'm going to talk a little bit more about actually using flood maps for decision making, and I'll do a little bit on machine learning and SmallSats at the end. For those of you who don't know about Cloud to Street, similar to a lot of the efforts proposed here, we also provide near real-time flood risk analytics. And we really focus on not just making flood maps, but packaging them into decision support tools and iterating with users on design so they can actually use them for a really specific decision use case. And I'll show an example of that in Republic of Congo, where we've been working in the past 3 years. So what we do is we ingest as many satellites as possible and optimize algorithms for each one. We mostly rely on Google Earth Engine, and then we cross that with impact information, and then send that information to users. And we sometimes also ingest crowd information from them as well into the dashboard and to feed back into our own algorithms. We've worked all over the world using flood maps for a variety of applications, but I'm just going to hone in on one country today to give you an example of sort of how this works with the Cloud to Street platform. So as you all know, flood maps can be used in every phase of the disaster cycle, and I'll show you an example of that, but not only for evacuation, for disaster relief, but also really understanding where floods happened in the past to improve preparedness and resilience. This is just an example of all the different satellites that we use. I think most of you are familiar with these, but we use both public and private satellites because some of the commercial and private satellites kind of here on the bottom that are at much higher spatial resolution are really needed in order to either increase frequency of observation when there's clouds or increase resolution to map floods in urban areas when public sensors just aren't really up to the task. So the story I wanted to tell about our work with the World Food Program in Congo, kind of in 3 phases of the disaster cycle. Some of you kind of know some of these stories before, but the first is how flood maps can be used for preparedness. So working with the World Food Program country director, they messaged us when refugee camps were moved onto the other side of the Congo River and wanted to know which one of those camps were at risk. And so we ran our algorithms back, as long as the satellite record affords, 30 years, and found that there was one community that had flooded at least 3 times and was actually starting to flood again, that we could see in PlanetScope imagery, just as the World Food Country Program Director messaged us. So we set them that information so that the Ministry of Social Affairs in the government could support relocation or recommend relocation for that refugee camp. And they're really glad that they did that, because just a year later, that same place flooded again, and a lot more people would have been affected had that refugee camp not been relocated. And so we supported World Food Program in their emergency response so that they could get the information in, or they could request the amount of aid that they needed and then direct that to the places that needed it the most across the country. But what we found was that in the long-term recovery process in Congo, what they really wanted to know was not just where are floods happening now, but how might they affect food security over the next 6 months so that we can provide cash-based transfers to support food insecure places in the country. So when we crossed flood maps with crop maps in Congo to try to answer that question, we found the public data on crop maps was horrible in this region. And there was no way we could provide reliable estimates. So we made our own machine learning based crop map at much higher accuracy to provide better impact assessments and help the World Food Program drive the cash-based transfers to those affected households. And this is kind of ongoing now, but there's actually more floods happening in Congo just over the past couple of weeks, and Cloud to Street is working with the World Food Program, helping response there, but I don't yet have kind of slides to tell you about that impact, but it's ongoing. Okay, so those are where flood maps can be used in the response, recovery, and preparedness phase of the disaster cycle. And I want to transition a little bit to some of our technical work coming out of our lab. And these are sort of the 3 insights that I want to leave you with. One is use SmallSats when you can. The increased coverage and resolution really makes a difference. And I'll show you an example of that. Invest in deep learning in the AI revolution. I know it sometimes seems like AI is a bunch of buzz hype, but it actually works. And I'll show you examples and some recent published papers that you can dig into to see where our experiments prove that, I think, pretty convincingly. And then third is practice human-centered design. This is a non-technical point, but I always get frustrated with the framing that users are some kind of last mile problem. That's not true. You actually need to start engaging with users at the very beginning. And it's exciting to be at GFP and kind of see scientists moving more and more in this direction of iterating with users as the first 100-mile part of the solution, not just someone that you talk to at the end after you make a flood map. So I'm really encouraged to see by all of that energy and effort in this community. Okay, a few key results, and I'm just going to send you to our papers for other details. The increased coverage that you get with SmallSats matters. If you link together Landsat 8, Sentinel-2, Sentinel-1, even MODIS, and look for where are places that you could see on a daily basis in a cloudy country like Sri Lanka over the rainy season, you're only gonna get clear coverage of the country, and this is including Sentinel-1 overpasses, about at about a 30% probability every day. If you use Planet, which gives you an image every single day, you're going to increase that coverage to almost 50%. So it nearly doubles the amount that you can see. And that really matters as floods are moving across a landscape and you're trying to catch maximum impact. The second is when you're thinking about the impact metrics that you're calculating. If we just look at, this is one of so many examples I could show, but the dam break in Michigan, just this past May, red is the flood footprint from Planet, blue is from Landsat. You would actually count a different number of buildings impacted and the economic financial cost totally differently if you were using Planet versus Landsat to make a flood map. So it matters. Second, a couple of points on machine learning. One of the coolest things about machine learning is that you don't have to throw away cloud and cloud shadow data. Machine learning algorithms are capable of parsing through that information. Normally in this kind of cloudy map, this is a Sentinel-2 map here, you would be throwing away all of this cloud and hazy area. But, and this is a random forest classification, you can actually see kind of some of these hazy areas here. You can make a pretty good water classification under thin clouds. And that's because shortwave infrared signals penetrate them effectively enough for an AI algorithm to pick up. So it's worth investing in. Convolutional neural nets will give you even more than a pixel-based approach like random forest. If you aren't familiar with these type of machine learning algorithms, what's really cool about them is they take into account the spatial context surrounding the pixel to make a decision. And so they're really good at identifying flooded objects instead of flooded pixels. And that yields pretty important gains in accuracy. We actually published and released a data set, a labeled data set on Sentinel-1 and Sentinel-2 to help the community inform development of and train deep learning algorithms for both optical and radar sensors. Check it out. You can download it for free. ESA also released recently SEN12 Flood, which is another labeled data set. So a lot of data is now available to support machine learning development. So I'm really excited to see the development of this community. This was just accepted last week, but we have it up on archive, so take a look and download it. One of the really big challenges of imagery like PlanetScope is it only has RGB and near infrared. And if you work with optical sensors, you know that the shortwave infrared band is really important to detecting water, but you don't get it with PlanetScope. And so it becomes really hard to see the difference in what is the cloud shadow versus what is water. But with machine learning, here we're using general adversarial networks, you can actually create a synthetic SWIR band by training PlanetScope on Sentinel-2 data when those two satellites overpass on the same day, and you can create this fake SWIR band to improve your flood predictions on PlanetScope. So that's what this paper walks through, the experiment and results of this method. And this is kind of a visual of what you can see. These are planet input images here on the left. This is the ground labeled data here in the second column. UNet is a really classically used machine learning algorithm. Doesn't do such a great job just using automated labels. But if you add in this synthesized, this fake SWIR band that we've made using general adversarial networks, and you include it in the model, H2ONet, this is our new algorithm, you can get a much better flood prediction that's gonna outperform traditional machine learning or just synthesizing or just thresholding on a SWIR band. So you've really gotta combine CNNs, convolutional neural nets together with general adversarial networks to get the best result in machine learning. You can check out our paper for more, but that's kind of the too long didn't read summary of that paper. You can increase accuracy of flood mapping on PlanetScope data 10 to 15%. And if you don't have enough labeled data, this is really important in machine learning. You've got to have a lot of data to train these models, but we're finding you don't have to have it be painstaking hand labels. You can use machine learning techniques like refiners to find the high probability flood areas and just use that to train the model instead, and that will increase your accuracy substantially. We've also done experiments on drone data. This works great for drones also, which are typically just RGBs. So check out that paper. The last latest paper that's come out of our lab that I want to talk about, this will be at the NeurIPS Climate Change AI workshop in a couple of weeks. But we're starting to do a lot more experiments with crowdsourcing data. And how do you conceive of using crowdsourcing data to update those machine learning algorithms you're using on a Sentinel-2 image, for example? So if you have social media points you're scraping versus a trained collector, say a team of citizens in a city that's taking photos, how do you use that to update your flood map? And how much more accuracy do you get? And the summary of this experiment is basically that with just a few ground points, this is 20 to 50 ground points, you can imagine that many people sending you photos around a flooded city, you can increase the accuracy of a convolutional neural network up to 5%. And this is kind of the result here where you can see refiner plus points. This is the crowdsourced data points. Outperforming just a traditional machine learning model that didn't have that new information to see small features. Check out our paper for more. And the last point I want to make about design, this is kind of my last point on not thinking about users as the last mile. They're the first 100 miles. One insight that we found, and Peter Solomon talked about this a little bit, is that maps actually are not enough to help people make the decision they need to make to use this information to make aid allocations. And so we have reworked our dashboard to stop just showing users flood maps and to calculating instantly the insight that they need, which is population and crops and roads affected and in what locations, kind of highlighting the affected areas in colors. And this came out of our iterative human-centered design process. Contact us if you would like to know more about that. And that's what I wanted to share. I think this is GFP is a really cool community where we think about how to compare our products together and make it more useful for users. I think I saw Lawrence on this call, but he led a paper. This is an idea that we hatched actually at GFP in China last year. Let's compare a flood model to flood observation frequency and understand their differences. So you can check that out in ERL, but this is the kind of thing that comes out of this community. And I hope these next sessions spur more of that type of collaboration so that we can work on flood resilience issues together. Thanks.
Thank you, Beth.